Hello and welcome. In this video, we will explore Maclaurin series, a fundamental concept in higher-level mathematics. By the end of this session, you will be able to, first, find Maclaurin series for composite functions using substitution. Second, perform arithmetic operations like addition, subtraction, multiplication, and division on Maclaurin series. Third, differentiate and integrate Maclaurin series term by term. And finally, apply these techniques to solve IB-style problems, including finding limits and approximating integrals. Let's begin by recalling the Maclaurin series for some common functions. These are the building blocks for everything we'll do today. The Maclaurin series for e to the power of x is the sum from k equals 0 to infinity of x to the k over k factorial. The Maclaurin series for sin ax is the sum from k equals 0 to infinity of -1 to the k times x to the 2k plus 1, all over 2k plus 1 factorial. And the Maclaurin series for cosine x is the sum from k equals 0 to infinity of -1 to the k times x to the 2k, all over 2k factorial. We will also frequently use the geometric series formula and the binomial series. The geometric series for 1 over 1 minus x is the sum from k equals 0 to infinity of x to the k, which is 1 plus x squared plus x cubed, and so on. This is valid for the absolute value of x less than 1. The binomial series for 1 plus x to the power of p is the sum from k equals 0 to infinity of p, choose k times x to the k, which is 1 plus px plus p times p minus 1 over 2 factorial times x squared, and so on. This is also valid for the absolute value of x less than 1. With these tools, we can now find series for more complex functions. Our first objective is to find Maclaurin series for composite functions using substitution. This is a powerful technique that allows us to build new series from known ones. Let's look at an example. Suppose we want to find the Maclaurin series for e to the power of 2x. We know the series for e to the power of x. The key idea is to replace every instance of x in that series with 2x. Here's the series for e to the x. We will substitute 2x for x. This gives us 1 plus 2x plus the quantity 2x squared over 2 factorial plus the quantity 2x cubed over 3 factorial, and so on. Simplifying this, we get 1 plus 2x plus 4x squared over 2 factorial plus 8x cubed over 3 factorial, and so on. This is the Maclaurin series for e to the 2x. Let's try another one. Find the Maclaurin series for cosine of x squared. We'll use the series for cosine x and substitute x squared for x. Substituting x squared for x, we get 1 minus the quantity x squared over 2 factorial, plus the quantity x squared to the 4th power over 4 factorial, and so on. Simplifying the exponents, we find the series for cosine of x squared is 1 minus x to the 4th over 2 factorial, plus x to the 8th over 4 factorial, and so on. Notice that all the powers of x are multiples of 4. This method is incredibly efficient. We have now seen how to find Maclaurin series for composite functions by substituting the inner function into the known series of the outer function. Next, we'll explore how to perform arithmetic operations on Maclaurin series. This allows us to find series for sums, differences, and products of functions. Let's start with addition and subtraction. The rule is simple. You can add or subtract series term by term, just like you would with polynomials. For example, let's find the Maclaurin series for sin x plus cosine x, up to the x to the 7th term. We write out the series for sin x and cosine x, aligning the terms by their powers of x. Now we add them vertically. The constant term is 1. The x term is x. The x squared term is negative x squared over 2 factorial. The x cubed term is negative x cubed over 3 factorial, and so on. We simply combine the coefficients of like powers of x. Multiplication is a bit more involved. We treat the series like polynomials and multiply them out, collecting terms of the same power. Let's find the first few terms of the Maclaurin series for e to the x times sin x. We write out the first few terms of each series. To find the terms up to x cubed, we only need to multiply terms that will result in powers of x up to 3. Multiplying the first term of e to the x, which is 1, by the terms of sine x gives x minus x cubed over 6. Multiplying the second term, x, by the terms of sine x gives x squared minus x to the fourth over 6. Multiplying the third term, x squared over 2, by the terms of sine x gives x cubed over 2. We can stop here, as any further multiplication will result in powers of x greater than 3. Now we collect the like terms. The x term is x. The x squared term is x squared. The x cubed terms are negative x cubed over 6 plus x cubed over 2, which simplifies to 2x cubed over 6, or x cubed over 3. So the first few terms are x plus x squared plus x cubed over 3. Finally, let's look at division. For division, we use a method called equating coefficients. We assume the quotient is a new series with unknown coefficients and then solve for them. Let's find the first three non-zero terms of the Maclaurin series for tangent x, which is sine x divided by cosine x. We start by writing the equation as sin x equals tangent x times cosine x. Then we substitute the known series for sine x and cosine x, and an unknown series for tangent x, which we'll call p of x. Now we multiply the series on the right side. We only need to go up to the x to the fifth term to find the first three non-zero coefficients. The final step is to equate the coefficients of the powers of x on both sides of the equation. For the constant term, 0 equals a 0, so a 0 is 0. For the x term, 1 equals a 1, so a 1 is 1. For the x squared term, 0 equals a 2 minus a 0 over 2, which means a 2 is 0. For the x cubed term, negative 1 over 6 equals a 3 minus a 1 over 2, which gives a 3 equals 1 over 3. For the x to the fourth term, 0 equals a 4 minus a 2 over 2 plus a 0 over 24, which means a 4 is 0. And for the x to the fifth term, 1 over 120 equals a 5 minus a 3 over 2 plus a 1 over 4, which gives a 5 equals 2 over 15. Substituting these coefficients back into our series for p of x, we find that the Maclaurin series for tangent x is x plus x cubed over 3 plus 2x to the fifth over 15, and so on. We have successfully performed arithmetic operations on Maclaurin series. Another powerful property of Maclaurin series is that they can be differentiated and integrated term by term. This means we can find the series for a derivative or an integral of a function by simply differentiating or integrating each term of its series. Let's see this in action. We know that the derivative of sine x is cosine x. Let's see if we can derive the series for cosine x by differentiating the series for sine x. Here's the series for sine x. We will differentiate each term with respect to x. The derivative of x is 1. The derivative of x cubed over 3 factorial is 3x squared over 3 factorial, which simplifies to x squared over 2 factorial. The derivative of x to the fifth over 5 factorial is 5x to the fourth over 5 factorial, which simplifies to x to the fourth over 4 factorial. And so on. The resulting series is 1 minus x squared over 2 factorial, plus x to the fourth over 4 factorial, and so on. This is exactly the Maclaurin series for cosine x. This confirms that differentiating term by term works. Now let's try integration. We know that the integral of cosine x is sine x. Let's integrate the series for cosine x to see if we get the series for sine x. Here's the series for cosine x. We will integrate each term with respect to x. The integral of 1 is x. The integral of x squared over 2 factorial is x cubed over 3 times 2 factorial, which is x cubed over 3 factorial. The integral of x to the fourth over 4 factorial is x to the fifth over 5 times 4 factorial, which is x to the fifth over 5 factorial. And so on. Don't forget the constant of integration, c. To find the value of c, we can set x equals 0. The integral of cosine x from 0 to 0 is 0. The series evaluated at x equals 0 is just c. Therefore, c must be 0. So the resulting series is x minus x cubed over 3 factorial, plus x to the fifth over 5 factorial, and so on. This is the Maclaurin series for sine x. We have now seen that both differentiation and integration can be performed term by term on Maclaurin series. Now let's apply these techniques to solve some IB-style problems. A common application is approximating definite integrals that are difficult or impossible to solve using standard integration methods. Consider the integral from 0 to 1 of cosine of x squared dx. This is a classic example of an integral that cannot be expressed in terms of elementary functions. The strategy is to replace the integrand cosine of x squared with its Maclaurin series and then integrate the series term by term. First, we find the series for cosine of x squared by substituting x squared into the series for cosine x. This gives us 1 minus x to the 4th over 2 factorial plus x to the 8th over 4 factorial, and so on. Next, we substitute this series into the integral. We can then integrate each term from 0 to 1. Evaluating the integral at the limits gives us 1 minus 1 over 10 plus 1 over 216 minus 1 over 9 360, and so on. This is an alternating series. To estimate the value correct to 4 decimal places, we need to use the alternating series estimation theorem. This theorem states that the error in approximating the sum of an alternating series is less than the absolute value of the first unused term. The first term we haven't used is 1 over 9 360, which is approximately 0.00068. Since this is less than 0.005, which is the maximum error allowed for 4 decimal places, we can stop at the third term. So we approximate the integral using the first 3 terms. 1 minus 0.1 plus 0.004626, which equals 0.904626. Rounding to 4 decimal places, we get 0.9046. This demonstrates how Maclaurin series can be used to find numerical approximations for integrals. Another important application of Maclaurin series is in evaluating limits of indeterminate forms, such as 0 over 0. Let's find the limit as x approaches 0 of the quantity e to the 2x minus 1, all divided by sine of 4x. If we substitute x equals 0, we get e to the 0 minus 1 over sine of 0, which is 1 minus 1 over 0, or 0 over 0. This is an indeterminate form, so we can use Maclaurin series. We'll replace the numerator and denominator with their respective Maclaurin series. For the numerator, we use the series for e to the 2x, which we found earlier, and subtract 1. For the denominator, we use the series for sine of 4x, which we find by substituting 4x into the series for sine x. Substituting these series into the limit expression, we get the limit as x approaches 0 of 2x plus 2x squared plus higher order terms, all divided by 4x minus 64x cubed over 6 plus higher order terms. Now we can simplify this expression. Since x is approaching 0, the terms with higher powers of x become negligible compared to the lowest power terms. We can factor out an x from both the numerator and the denominator. This allows us to cancel the x terms. The expression becomes the limit as x approaches 0 of 2 plus 2x plus higher order terms, divided by 4 minus 64x squared over 6 plus higher order terms. Now, as x approaches 0, all the terms containing x go to 0. We are left with 2 divided by 4, which simplifies to 1 over 2. This shows how Maclaurin series can be used to evaluate limits without using L'Hopital's rule. Let's tackle a more complex problem that combines several of the techniques we've learned. We'll find the Maclaurin series for e to the power of cosine x. Our goal is to find the Maclaurin series for e to the power of cosine x up to the x to the 4th term. This is a composite function, e to the power of u, where u is cosine x. We'll use substitution, but first we need to expand the inner function, cosine x. The series for cosine x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on. We will substitute this entire expression for x in the series for e to the x. The series for e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. We will replace every x with the series for cosine x. This gives us 1 plus the quantity 1 minus x squared over 2 factorial plus the quantity 1 minus x squared over 2 factorial squared over 2 factorial plus the quantity 1 minus x squared over 2 factorial cubed over 3 factorial, and so on. Now, we need to expand each of these terms and collect the coefficients of x to the 4th. The first term is 1. The second term is 1 minus x squared over 2 plus x to the fourth over 2. The third term is 1 minus x squared over 2 squared, all over 2. Expanding the numerator gives 1 minus x squared plus x to the fourth over 4. Dividing by 2 gives 1/2 minus x squared over 2 plus x to the fourth over 8. The fourth term is 1 minus x squared over 2 cubed, all over c. Expanding the numerator gives 1 minus 3x squared over 2 plus higher order terms. Dividing by 6 gives 1/6 minus x squared over 4. The fifth term is 1 minus x squared over 2 to the fourth, all over to 4. The constant term is 1 over 4, and the x squared term is negative 4 times x squared over 2, all over 4, which is negative x squared over 12. Now we collect all the terms up to x to the fourth. The constant term is 1 plus 1 plus 1/2 plus 1/6 plus 1 over 4, which sums to 2.71875. The coefficient of x squared is negative 1/2 minus 1/2 minus 1/4 minus 1/12, which sums to negative 125. The coefficient of x to the fourth is 1 over 4, plus 1/8 plus 1 over 16 minus 1 over 12, which sums to 0.45833. So, the Maclaurin series for e to the power of cosine x up to the x to the fourth term is approximately 2.71875 minus 1.25 squared plus 0.4583x to the fourth. This is a complex but systematic process. Let's conclude with a historical note and a beautiful result from Euler. We will use Maclaurin series to prove that the sum of the reciprocals of the squares of the natural numbers is equal to pi squared over 6. This is known as the Basel problem, and Euler's solution is a classic example of the power of series. The proof starts with the Maclaurin series for sine x. We know that sine x equals x minus x cubed over 3 factorial, plus x to the fifth over 5 factorial, and so on. Now, let's divide the entire series by x. This gives us sine x over x equals 1 minus x squared over 3 factorial, plus x to the fourth over 5 factorial, and so on. This function is well behaved at x equals 0, where its value is 1. Next, we consider the zeros of the function sine x over x. The zeros of sine x are at x equals n times pi, where n is an integer. However, the 0 at x equals 0 is removed by the division by x. So, the zeros of sine x over x are at x equals plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, and so on. Euler made a bold claim. He said that just as a polynomial can be factored into terms involving its roots, an infinite series can be factored into terms involving its zeros. So he proposed that sine x over x could be written as an infinite product. 1 minus x over pi times 1 plus x over pi times 1 minus x over 2 pi times 1 plus x over 2 pi, and so on. We can group these terms into pairs using the difference of squares formula. A minus b times a plus b equals a squared minus b squared. This simplifies the product to 1 minus x squared over pi squared times 1 minus x squared over 4 pi squared times 1 minus x squared over 9 pi squared, and so on. Now we have two different expressions for the same function, sine x over x. One is a series, and the other is a product. We can equate them. We have the series on the left and the product on the right. The key to solving the Basel problem is to compare the coefficients of the x squared term on both sides. On the left side, the coefficient of x squared is negative 1 over 3 factorial, which is negative 1/6. On the right side, to get an x squared term, we must multiply the 1 from every term except 1, and from that one term, we take the x squared part. So, the coefficient of x squared is negative 1 over pi squared minus 1 over 4 pi squared minus 1 over 9 pi squared, and so on. Now we equate these two coefficients. We have negative 1/6 equals negative 1 over pi squared times the sum of the reciprocals of the squares. We can cancel the negative signs and multiply both sides by pi squared. This gives us the sum of the reciprocals of the squares equals pi squared over 6. This is a beautiful and unexpected connection between pi and the sum of an infinite series. We have now covered the key techniques for working with Maclaurin series. Let's recap what we've learned. We started by finding series for composite functions using substitution. We then learned how to add, subtract, multiply, and divide series. We saw that we can differentiate and integrate series term by term. Finally, we applied these methods to approximate integrals, evaluate limits, and even prove a famous mathematical identity. These skills are essential for the IB/AHL curriculum. Now, let's test your understanding with some practice questions. Here are 5 practice questions designed to reflect the style and difficulty of the IB/AHL exam. Pause the video and try to solve them on your own. After you've finished, you can resume to see the fully worked solutions. Question 1. Find the Maclaurin series for sine of 2x up to the x to the 5th term. Question 2. Find the Maclaurin series for e to the x times cosine x up to the x cubed term. Question 3. Find the Maclaurin series for 1 over 1 plus x squared up to the x to the 4th term. Question 4. Use the result from question 3 to find the Maclaurin series for arctan x up to the x to the 5th term. And question 5. Find the limit as x approaches 0 of the quantity 1 minus cosine x all over x squared. Take your time and work through these problems. Good luck! Welcome back. Let's go through the solutions together. First, question 1. We need to find the Maclaurin series for sine of 2x up to the x to the 5th term. We start with the known series for sine x. We then substitute 2x for x. This gives us 2x minus the quantity 2x cubed over 3 factorial, plus the quantity 2x to the 5th over 5 factorial, and so on. Simplifying the terms, we get 2x minus 8x cubed over 6, plus 32x to the 5th over 120. This simplifies to 2x minus 4x cubed over 3, plus 4x to the 5th over 15. This is the Maclaurin series for sine of 2x up to the x to the 5th term. Now for question 2. We need to find the Maclaurin series for e to the x times cosine x up to the x cubed term. We write out the first few terms of the series for e to the x and cosine x. We multiply these two series like polynomials, collecting terms up to x cubed. Expanding this, we get 1 minus x squared over 2, plus x minus x cubed over 2, plus x squared over 2, plus x cubed over 6, plus higher order terms. Collecting the like terms, the x squared terms cancel out. The x cubed terms combine to negative 1/3 x cubed. So, the series is 1 plus x minus x cubed over 3. This is the Maclaurin series for e to the x cosine x up to the x cubed term. Let's move on to question 3. We need to find the Maclaurin series for 1 over 1 plus x squared up to the x to the 4th term. We can use the geometric series formula here. The formula is for 1 over 1 minus r. We can rewrite our function to fit this form. We can write 1 over 1 plus x squared as 1 over 1 minus the quantity negative x squared. Now we can use the geometric series formula with r equals negative x squared. Substituting negative x squared for r, we get 1 plus negative x squared, plus negative x squared squared, plus negative x squared cubed, and so on. Simplifying the terms, we get 1 minus x squared plus x to the 4th minus x to the 6th, and so on. The Maclaurin series for 1 over 1 plus x squared up to the x to the 4th term is 1 minus x squared plus x to the 4th. Now for question 4, which builds on the previous one. We need to use the result from question 3 to find the Maclaurin series for arctan x up to the x to the 5th term. The key here is to remember the relationship between arctan x and the function from question 3. The derivative of arctan x is 1 over 1 plus x squared. This means that arctan x is the integral of 1 over 1 plus x squared. We can find the series for arctan x by integrating the series we found in question 3 term by term. We integrate the series 1 minus x squared plus x to the 4th, and so on. The integral of 1 is x. The integral of negative x squared is negative x cubed over 3. The integral of x to the 4th is x to the 5th over 5, and so on. We also have a constant of integration, c. To find c, we can use the fact that arctan of 0 is 0. If we plug x equals 0 into our series, we get c. Therefore, c must be 0. So, the Maclaurin series for arctan x up to the x to the fifth term is x minus x cubed over 3 plus x to the fifth over 5. This is a classic result. Finally, let's look at question 5. We need to find the limit as x approaches 0 of the quantity 1 minus cosine x, all over x squared. This is another indeterminate form, 0 over 0. We will use Maclaurin series to solve it. We start with the Maclaurin series for cosine x. We then substitute this into the numerator. Now we substitute this expression back into the limit. We have the limit as x approaches 0 of x squared over 2 factorial minus x to the fourth over 4 factorial, and so on, all divided by x squared. We can simplify this by dividing every term in the numerator by x squared. This gives us the limit as x approaches 0 of 1 over 2 factorial minus x, squared over 4 factorial, plus x to the fourth over 6 factorial, and so on. As x approaches 0, all the terms containing x go to 0. We are left with 1 over 2 factorial, which is 1/2. This is a very useful limit to remember. That concludes our deep dive into Maclaurin series. We've covered the essential techniques and applications required for the IBAAHL curriculum. You should now be comfortable with substitution, arithmetic operations, differentiation, and integration of series. You can use these tools to approximate integrals, evaluate limits, and solve a variety of problems. Keep practicing these techniques to build your mastery. Thank you for watching.